Okay, so we'll start with BVLSI lecture number 39. So yesterday we have seen the general shape of a VTC curve. I am redrawing it over here. So this is my V in, this is my V out, and the general nature of the VTC curve is like this. For very low input, output is high, and for high value of input, the output is low. So out of this we mark two critical parameters, VIL and VIH. How do we mark it? We take the slope as -1. Alright, so this is slope equal to -1 over here and -1 over here, and this point we extend it to the x-axis and call this as VIL and VIH. Alright, this is my VTC curve. So today we are mathematically justifying why we take it at -1 slope. So today we will justify the selection of VIH and VIL using the slope condition. What is my slope condition? dV out by dV in is equal to -1. Alright. So basically the output of a inverter under noise free steady state conditions is a non-linear function of input. As you can see, the output is a non-linear function of input. It's not at all linear. You can it's elaborate from the shape of this VTC curve. So we can say V out is a function of V in, but it's non-linear, highly non-linear. Okay, this we call it equation number 1. Now over here, if the input signal is disturbed from its nominal value because of external factors such as noise, the output will deviate from its nominal value, yes or no? So let's say the noise will affect the system. Noise will enter the input. So definitely there will be a disturbance in the output also. So what will be the modified output given by V out dash will be equal to function of V in plus noise, delta noise, which this is very small. So delta noise represents the voltage perturbations that is assumed to affect the input voltage of the inverter. So write down V out dash is disturbed or perturbed output voltage. So do you know Taylor series? So we'll use Taylor series expansion first order. Using first order, okay, Taylor series expansion on equation number 2. So equation number 2 becomes V out dash is f of V in plus dV out by dV in, yes or no, into delta V noise plus high order terms, delta V out square upon dV in square, delta V noise square, right? I am writing it as higher order terms, which we will neglect it in this case because delta noise will become very small. So that will be very close to 0. So the higher order terms are neglected. Let's call this equation number 3. Now if you see carefully, I can write V out dash as function of V in. V out should be a function of V in only, right? It should not be a function of noise, correct? So I'll get this equation now. V out dash is function of V in plus dV out by dV in into delta V noise. I'll put this equation under the box and I'll call it equation number 4. So what does f of V represent? It represents the nominal output voltage, undisturbed or non-perturbed output signal. Function of input, that is output signal, nominal output signal. What is dV out by dV represents? Anyone? It represents the voltage gain of the inverter. Gain of the inverter is output upon input, right? So it represents the voltage gain of the inverter at the nominal input voltage. Okay? Yes or no? The same equation we can represent it as follows. This can be written as, same equation I can write it over here. Perturbed output is equal to nominal output plus gain into external disturbance. Yes or no? Perturbed output is V out dash, nominal output is function of V in, dV out by dV in is gain, and delta V noise is external perturbation. Okay? Now there are few observations related to equation number 4. So let's write them down. Understood this? If I take the magnitude, I'll write it over here. If I take the magnitude of the voltage gain smaller than unity, then what will happen? If dV out by dV in is less than 1, will it get amplified? The noise will get amplified. ये gain है ना? अगर gain is less than 1, it's not an amplifier, right? It's an attenuator. So if dV out by dV in is less than 1, V out almost equals to function of V in. Yes or no? Because these are not amplified. Plus a small value of dV up noise, because this is less than 1, right? In the second case, if the gain dV out by d in is greater than 1, then what will happen? There will be a large perturbation in the output. So it will be a function of V in plus same formula. So the factor of noise will affect the output very much. Yes or no? So it will amplify the noise. So this will amplify. This will act as an amplifier now. Gain with greater than 1, right? Amplify the noise signals. This is not at all recommended. Therefore, okay, so it should be less than 1, so it will not be amplified. If it is greater than 1, it will be amplified. So what it should be? Therefore, we define the boundaries for the valid input region as the voltage point where the magnitude of the voltage gain is exactly equal to 1. So if I take over here third case, dV out by dV in equal to -1, what will happen? What will happen to equation number 4? V out dash will become f of V in minus noise. So noise voltage gets cancelled out. That is good or bad? That is very good. Effect of the noise is getting reduced. So that's why we take dV out by dV in as -1. Gain with -1. That's why we consider the two critical parameter slope dV out by dV in as -1. Understood now? This is a justification for taking dV out by dV in as -1 and not at any other value. It cannot be 1 also. So if this is taken, then V out dash will be function of V in minus the noise fluctuations. Therefore, the magnitude of the voltage gain should be -1. That's why we take this on VTC curve to select input low voltage and input high voltage, VIH and VIL points. Yes or no? Understood now? That is why we select on the VTC curve these points, right? This is VIL, VIH, where the slope is -1. So dV out by dV is also called as slope, also called as gain. So now on, for any inverter circuit, our focus is to find 5 critical parameters. On the VTC curve. So which are the 5 critical parameters? VOL, VOH, VIL and VIH and VTH. That will fully describe my DC input output characteristics of my inverter, and it will tell me the location of noise margin levels. So our goal is to accurately estimate these critical parameters and the noise margin levels. What are the 2 noise margin levels? Noise margin high and noise margin low. And this has to be done for which all inverters we will study in detail. Number 1, resistive load NMOS inverter, PMOS load NMOS inverter, which is CMOS inverter. So we have detailed analysis for them plus numericals, whereas we have comparison for enhancement and depletion load. We have just the comparison, no analysis for enhancement and depletion load. Alright? Now we'll talk about a bit of power consumption and chip area. Completed? So this is what will our aim is, to find these critical parameters, noise margin levels for these 2 inverters, resistive load and CMOS inverter, and then compare all the 4 inverters. Actually that is experiment number 2, right? Comparison of 4 inverters. Alright, let me use that PDF. So if you want to read further, you can refer this document, prep document. It's all written over here, okay? Alright. So next we talk about power and area consideration. So let me read out from this PDF. So power and chip area occupied by the inverter circuits are 2 major issues that play significant roles in inverter design. There can be a power hungry application. Let's say in gaming application, we don't worry about how much power we lose. We only worry about the performance and the speed. It should be fast enough. Whereas sometimes for power critical application like a pacemaker, which will replace the heart, right, in some patients, so their power consumption is very important. Speed doesn't matter, speed can be slow, but एक बार power अगर बराबर नहीं है, if it slows down, then it may be threaten the health of the person. So that's why there are 2 design approaches. One is power, one is speed. So about 1 million, right now it's billion logic gates can be accommodated on 0.5 micrometer technology. Now, right now, how much is going on? Less than 15 nanometer technology, actually even lesser than that. So each gate on the chip dissipates power and generate heat, yes or no? Maybe it's a microwatt or picowatt power, but it will dissipate and generate heat. So removal of this thermal energy that is cooling the chip becomes extremely important and expensive. Do you remember the old desktops used to come with 3 fans? One in the CPU, one in the motherboard and one in the power unit. Yes or no? Why reduce power? Because most portable devices such as cellular phones, laptops operate from a limited power supply. Yes or no? So the extension of the battery operation or battery operation time is important. You want your mobile phone battery to work as long as possible. If it consumes more power, if it should work for let's say 24 hours, it will work less than 10 hours. Okay? So that is a significant design goal. Therefore, it is very, very important to reduce the amount of power consumed in both DC and dynamic operation. Okay? So what is the DC power dissipation given by IDC into VDD? Write this down. DC power dissipation is given by the amount of current from the power supply during steady state and the power supply voltage. VDD is the power supply voltage, IDC is the amount of current drawn from the power supply during steady state. Remember, this current for the inverter will depend upon the input and output voltage levels. Okay? Written the formula? Now, listen carefully. Assuming that input voltage level is 50% of the time logic 0, other 50% of the time logic 1. So both are taking 50% operation. So during that time, my overall power dissipation will be given by VDD by 2. ID when V in is low matlab VIL, and ID when V in is high matlab VIH. समझ में आया? Why VDD by 2? Half power when input is low, half power when input is high. So that's why this formula, write it down. So the overall power consumption of the circuit will be VDD by 2, ID current into when the input is low plus current when the input is high. So this power dissipation will be different for different inverters. So the selection of the inverter also depends upon the power dissipation, DC power dissipation. Alright? Chip area. How do we reduce the chip area? By reducing W and L. We are doing that by scaling. When will you say minimum transistor area? If I reduce the area, let's say W is 100 micrometer. If I reduce W by L, W into L into 100 nanometer. If I take W and L both same, can I say W by L ratio is unity? If W and L is both same, W by L is unity, na? So this is achieving minimum transistor area is achieved when W and L are same. Okay? Fine? Yeah, that's it. Now we are going to start with actual MOS inverters. So write down. MOS inverters classification. Actually we have classified it, but let's see. MOSFET inverters. There are two types of analysis which we do over here. One is called as steady state or static analysis. One is called as dynamic analysis. In static analysis, actually we find out the critical parameters. We'll estimate the critical parameters. What are the critical parameters? VOH, VOL, VIH, VIL and VTH. Then we determine the noise margins, right? From these critical parameters, what do we find? Noise margin levels, which are noise margin low, noise margin high. Then from this further, we calculate DC power dissipation. Which is called as PDC or P average, whose formula you have written just now. So this is static analysis. Do you have both in your subject? In your syllabus you have static analysis and dynamic analysis both. Okay. Under dynamic analysis you have propagation delay estimation, which is nothing but tau p HL, low to high propagation delay and high to low propagation delay and average propagation delay. Next, we calculate dynamic power dissipation. This is also very important. Static power is when we are not using a mobile phone at all. Dynamic power is when you are using it, you are calling it, you are playing an app, you are listening to music. That is dynamic power. So we have both the analysis for which inverters we have to do? Resistive load and CMOS inverter. We have to do a detailed analysis for these two. So can we start with resistive load now? Written. Let us start. Let's draw resistive load NMOS inverter. First of all, we'll draw its circuit diagram. Use enhancement symbol. And the load over here is resistive. Here the input is measured across this V in and output is measured across the drain terminal. This is V out. With respect to ground, of course, this is drain, gate, source, body. Okay, this is the load RL. Current flowing over here is IRL, right? And current flowing into the device is ID. So which is the transistor used over here? NMOS driver transistor, enhancement type. Yes or no? Which is the load over here? Linear resistor. It's a linear resistor, right? Why linear? Because V equal to IR is followed. Ohm's law is followed over there. Transistor is a non-linear device. This is non-linear. So from the circuit, you have drawn the diagram. Can I say this is VGS? See this. And this voltage over here to here is VDS. So what can I write over here? Can I say from the circuit, VGS is equal to V in? Can I say that, yes or no? And what is VSB? 0. What is VDS? Or output, right? Agree? So the threshold voltage of the MOSFET is VTO, without substrate bias effect. So write down, let's start writing. You have drawn the diagram. These are the observation points which you have to write. Under steady state conditions, can I say ID is equal to ID IRL? Are incoming current is equal to outgoing current, no? What is ID? Drain current of driver NMOS. And what is IRL? Load current. Now let's draw the VTC curve for resistive load. The VTC curve will look like this. It will not go to 0. So VOL is non-zero, this is VOH. This point is VIL and this point is VIH. How do I mark VTH? Come on, tell me, how do I mark VTH? I'll draw a line, straight line, V in equal to V out line, right? And where it will intersect this graph, this is called as VTH. So this is my VTC curve for resistive load CMOS inverter. Now let's write down the equation of the current and the voltage conditions for NMOS driver. Ready? See, for resistor we don't do anything. The current passing through the resistor will dissipate the power. That's it. Okay, write down operating regions of NMOS driver transistor. This you will tell me. Okay, tell me when the driver is off. Current is 0. What is the condition of the voltage? VGS is less than VTO. Agree? When it is in the linear region, tell me the condition over here of voltage. Okay? And the current? The voltage here. Yes or no? This is the condition on the voltage. What about the equation? Kn by 2 twice VGS minus VTO into VDS minus VDS square, right? Where Kn is okay. Next is ID SAT. Kn by 2 VGS minus VTO square. Here we are assuming lambda equal to 0. Write that down. Assumption में lambda is 0. So lambda is 0 मतलब 1 plus lambda VDS term will not come here, right? और एक term होता है ना 1 plus lambda VDS, that will not come. What is the condition? Actually greater than equal to लिखो. What is equal to condition called as edge of saturation? And what is greater than condition called as VDS greater than VGS minus VT? Beyond saturation. So here my NMOS is in linear region and here NMOS is in saturation region. Agree? Okay, now let's work with numbers. I'll use my old PDF now. Completed the operating regions of the NMOS driver. or let me work here only, no problem. I will explain you analytically with numbers the working of this NMOS inverter. So let's start with working with numbers. No need to write it, just listen. So case number 1. Okay. So this is my VTC curve. ऐसे ही है ना, V in, V out. Let's say this is 5 volt. Okay, and let's say input is around 0.5. यहाँ पे input मेरा 0.5 में. So what is my let's say VTO is 0.5, VDD is 5. So for input for V in less than 0.5, what is V in? VGS ना, लिखा था ना, V in is equal to VGS. So for VGS less than VTO, what will happen? NMOS is off. So ID is 0. If ID is 0, this is my condition now, ID is 0, this will act as an open switch. Yes or no? So what will be my V out? V out will be equal to VDD. Some amount of current will flow, but it will be almost equal to VDD, because ID is 0, right? So no voltage drop across this. Output will be pulled up towards VDD. So here I can say no voltage drop, ID is 0. So no voltage drop across RL. This NMOS is off, represented by open circuit. And so we can say V out is equal to VDD. वही तो है ग्राफ में, देखो, this is VDD only ना. Understanding? Now let's say ये समझ में आया. Next case. Let's say that you are operating over here. At 2 volt. 2 volt में ऑपरेट कर रहे हो, ये 2 volt है. And let's say this value over here कम हो गया ना थोड़ा आउटपुट. This is 5. This, let's say this is 4.5, ये dotted level at the output. Okay. So here what is V in? अरे बताओ ना, 2 ना. So can I say 2 volt VTO कितना था? 0.5. Is 2 greater than 0.5? Yes. और एक कंडीशन चेक करना है, कौन सा? What is VDS? V out ना, ये 4.5 है बराबर ना आउटपुट में से. And what is VDS? V out. So is my VDS greater than VGS minus VTO? चेक करो. This is 4.5 greater than 2 minus 0.5. Is it true? Yes. So my NMOS is working in the saturation region. So current flows, ID will flow. So your circuit will look like this, almost like a short circuit, and the current will flow and output will slowly fall down. It's falling down, right? Here NMOS is on. Okay, here is RL. So why the output will drop? Because it will drop across the NMOS driver. So slowly it will go. So यहाँ पे क्या हो रहा है? Two things to note down. NMOS is not in linear region, directly saturation में जा रहा है cut off के बाद. After cut off it goes to saturation, and output is slightly even reducing from 5 to 4.5. So still it is output high ना. 4.5 still considered high. समझा ये? Now let's say इसमें समझा रहा हूँ. थर्ड केस में 3.5 हो गया, तो 3.5 वोल्टेज इधर आ गया. लेट्स से ये 3.5, राइट? Here my output is what? 0.5 volt. Let's say Okay, so now V in is what? 3.5, right? So VGS greater than VTO condition satisfy हुआ क्या नहीं? Yes. What is my output here? 0.5 ना, तो VDS कितना है मेरा? ये 0.5 है और ये कितना है? This is 3.5 minus 0.5, 3. So क्या साइन आएगा? लोअर. So my NMOS is working in the linear mode of operation. तो ये इंपॉर्टेंट है, ये अंडरस्टैंड करना है. दिस विल हैपन ओनली विद नंबर्स. बट स्टिल आईडी यहाँ पे क्या फ्लो हो रहा था? आईडी सैट फ्लोज. यहाँ पे आईडी लीनियर फ्लोज, बट इज कंटिन्यूस टू फॉल डाउन. आउटपुट इज स्टिल reducing. So this explains the working of NMOS driver of the circuit. Alright. Now I will tell you the input voltage ranges. ये समझ में आया पूरा working with numbers? Now write this down, the table. Input voltage range NMOS driver operating mode. चलो फर्स्ट केस में इनपुट वोल्टेज रेंज इज V in less than VTO. बताओ NMOS is in, बताओ कट ऑफ. नेक्स्ट केस में V in is between V out plus VTO. थर्ड केस इज V in is greater than or equal to V out plus VTO. अरे घबराओ मत, V out इज VDS ना. ये देखो, आई कैन रिफ्रेम दिस इक्वेशन, राइट. मैं एग्जांपल बताता हूँ. ये V in, ये वाला मैं कैसे लिखता हूँ बताओ. ये देखो, दिस इज VGS ग्रेटर देन और इक्वल टू VDS प्लस VTO. बराबर है? यस और नो? हाउ कैन आई राइट दिस नाउ करेक्टली? VDS इज, ये दोनों सेम है ना. ये कौन सा कंडीशन है? NMOS in linear, तो ये कंडीशन इज लीनियर. बराबर ना? Now how will you translate this? एक है V in ग्रेटर देन और इक्वल टू VTO. ये VGS वाला कंडीशन है, राइट? करेक्ट ना? सेकेंड कंडीशन क्या है? तो ये क्या है? VGS लेस देन. सो कैन आई से VDS इज ग्रेटर देन VGS माइनस VTO. ये कौन सा कंडीशन है NMOS का? सो हियर इट इज इन सैचुरेशन. आर यू एबल टू अंडरस्टैंड? तो ये मेरा इनपुट वोल्टेज रेंज है. दिस टेबल इज वेरी वेरी इंपॉर्टेंट. इफ यू अंडरस्टैंड दिस टेबल, योर वर्किंग विल बी ओवर. आई मीन ओवर इन द सेंस यू विल अंडरस्टैंड एवरीथिंग. The same way we have the CMOS inverter. Completed and understood this very well with numbers. If you want to explain, use numbers. Automatically everything will be clear to you. It's all about in which operating mode my NMOS driver is. It's in the cutoff, saturation or linear. तीन ही mode है. And resistor is तो linear device. Yeah, sure. Understood now how it translates into VGS and VDS? Yeah. So we stop the lecture over here. I'll tell you what you will do next time, preview of it. So next time we'll start with next lecture will estimate the expressions of VOH, VOL, VIH, VIL and noise margin levels of this inverter. So this we will do derive this expressions for all these volt critical parameters and write the expressions for the noise margin levels, and we'll solve a numerical, analytical numerical and design numerical. So that is what we will do next time. So that's it for today.